All right, welcome to 3.3 notes. We're talking about graphing rational functions today. In order to graph rational functions, we need to know how to find several things. So that's going to be the main focus of today's lesson. So a rational function is a function that you can write in the form f of x is equal to p of x over q of x, where p of x and q of x are polynomial functions. That only means that p of x and q of x are functions that have x in them. So if you look at the three examples here, we've got an x on the top and x on the bottom, x is on the top, x on the bottom, x on the top, x on the bottom. So your top and bottom of your function all have x's in them. The domain of f of x is all real numbers except those values for which q of x, which is the denominator, equals 0. Because then, again, if we were to replace q of x with a big 0, we'd have p of x divided by 0. Can we divide by 0? I did not think so. So, why you cannot divide by 0? All right, so here are the graphs of three rational functions. We are used to seeing graphs that look like this. That's what our previous two lessons have kind of shown us. However, we're going to learn in the next couple of lessons how to graph things that look very different than that and why those things occur. So for the first rational function, y is equal to x squared over x squared plus 1, there's no value of x that makes the denominator 0. If we look at that, the denominator is x squared plus 1, x squared plus 1. If we wanted to see where that equals 0, we can subtract 1 from both sides, and we get that x squared is equal to negative 1. Now, x squared can never equal negative 1 because x is being squared. And anytime you square any number, you end up with a positive answer. Negative 4 squared, for instance, is positive 16. Negative 1 squared is positive 1. You cannot get a negative number by squaring a number. So therefore, you can't get this equal to 0. It just doesn't work. So this type of function has no holes, jumps, or breaks, and is called a continuous function. In the second graph, y equal to x plus 3 times x plus 2 divided by x plus 2, x cannot equal negative 2, or the denominator would equal 0. If we look at that real quick, if x equaled negative 2, we'd have y is equal to negative 2 plus 3 times negative 2 plus 2 over negative 2 plus 2. And if we look, you should notice negative 2 plus 2, we know that math, that's 0. And then we'd have 0 in the denominator. We cannot divide by 0, so therefore x cannot equal negative 2. In the third graph, y equals x plus 4 over x minus 2, x cannot equal positive 2, or the denominator would equal 0, for the same reason. Because if we plugged in 2, we'd end up with y is equal to 2 plus 4 over 2 minus 2. And again, we know this math, 2 minus 2 equals 0. We cannot divide by 0, so therefore we cannot have a value of 2 in for x. This type of graph always has at least one hole, jump, or break, and is called a discontinuous function. Okay, so if we look, we have a hole here, causes a discontinuity, and here we've got a jump or a break. We know it as an asymptote. This vertical asymptote here is what's causing our break in our graph. It's causing our discontinuity. The whole jump or break is called a, as I just said, discontinuity. The second graph, let's go back to the second graph here, remind ourselves how that looks. Y equals x plus 3 times x plus 2 over x plus 2 has a removable discontinuity. because both the numerator and the denominator contain x plus 2 as a factor which can be divided out. If we look, that x plus 2 that was on the bottom can actually be divided out with the one on the top. That's why we call it a removable discontinuity. And yes, it does give us the graph of y equals x plus 3. If we look here, is exactly what this graph is. It's a linear function, and it's the function going through the y-intercept of 3, or 0, 3, and the graph has a slope of 1, which is y equals x plus 3. We know what that looks like. However, it has this hole still, because if you put it into the function, you can't get rid of it. The discontinuity exists. We mark that hole with a little circle. We don't ever want to forget that hole. Call it a removable discontinuity because it can be divided out. The third graph, x plus 4 divided by x minus 2, has a non-removable discontinuity. Because the numerator and the denominator have no common factors that can be divided out. If we look here, the numerator and the denominator, no common factors. We cannot divide anything out, so therefore there's no holes in our graph. The x minus 2 being in the denominator is what is causing our vertical asymptote. All right.